A common question that a lot of people ask in quantum mechanics is what does the wave function psi actually mean? Because, psi of x squared gives us the probability of finding the whatever it is, whether it be an electron or a proton or whatever being described by psi at a specific position x. This gives us the probability of it. But what is psi of x? Just psi of x. It's kind of something that doesn't really, that eludes definition, if you will. Well, I guess the best definition that I've ever been able to come up with was that psi of x describes all spatial properties of the electron or the proton or the neutron. And these properties could be the momentum, the orbital angular momentum, the kinetic energy, the potential energy, etc. Keep in mind here that I have psi of x. I could likewise have psi of xy or psi of xyz, depending on how many dimensions that I have. I'm just using one dimension for simplicity. But the key thing to note here is that the particle actually behaves as if it is distributed according to the wave function. So, for instance, to illustrate this, I could say that the charge of an electron is actually distributed, so this is the charge distribution, is actually distributed as Q, which is the fundamental charge, times psi of x squared, the magnitude of psi of x squared. Or I could say the mass of the electron is distributed as m times the wave function's magnitude squared. Now, when you localize you say, well, how can, an electron is a point particle when I make an observation? Well, that is true. Well, quantum field theory does say that you can never completely localize an electron. But when you do make a measurement, essentially your wave function collapses into a delta function. So if I am plotting here x versus psi of x, this could be some crazy function. Let's say it's like that. But when I make a measurement, psi of x collapses into a Dirac delta function. So let's say that I made the measurement at x equals 2. Then I'll have a delta function there, and it will be completely localized. So after I make the measurement, then the particle will start to spread out according to the rules of Schrodinger's equation. And so you'll see a slight spread out, like that. So this is basically how I understand a wave function. It is almost purely a mathematical construction, but the key point to realize is that the particle actually behaves as if it is distributed in space, and that is something that is very shocking. It goes against all classical notions, and it is what makes quantum mechanics so mysterious and strange.